I will be presenting today my paper titled Evolutionary Optimization of Building Envelope Design with Photovoltaics-Integrated Shading Devices. And what I present today is an evolutionary optimization tool that is extended from a tool developed previously by me and my author, titled Multi-Objective Design Optimization of Building Space Layout, Energy and Daylighting Performance, that was published very recently at Journal of Computing in Civil Engineering. You can find it online. And the tool supports early design decisions that have an influence on performance, such as building energy consumption and photovoltaics electricity generation, as well as daylighting performance. And I will first explain the model, the tool that we developed, and then I will present a comparative analysis on a number of building forms and photovoltaics usage. So shading devices are being increasingly used in performative buildings. They help control solar gains and reduce cooling loads during summer and the associated energy use resulting from solar radiation. They also mitigate the negative consequences of direct sunlight. They improve visual comfort when used as the primary lighting source, and as a result they reduce energy consumption due to artificial lighting, and finally they allow for larger openings to increase visual access. Photovoltaics are also being used as integrated to shading devices. Very typically they are either attached to the glass panels from the reverse side, or they are laminated to the they laminate the cells between two sheets of glass, and you can see several applications of this kind of photovoltaics installations on the shading devices. Currently, the most common use is rooftop photovoltaics. As you can see to the left and to the right, you will see the average sum of global irradiation per square meter received by PV modules. And you will see that the horizontal plane still receives the majority of sunlight. But you can also see that there is much potential that can be fulfilled on vertical facades as well. So the main motivation was that photovoltaics integrated shading devices is a multi-objective decision problem, such that energy consumption should be minimized, both cooling and heating. Electricity generation by photovoltaic panels should be maximized, and daylighting should be optimized, meaning the required illumination set point should be met. So we implement evolutionary multi-objective optimization, and as I mentioned, there is a tool that we previously developed, and we adapted this tool to integrate shading devices and photovoltaics as attached to these shading devices. And we use an SGA2, a non-dominated sorting genetic algorithm tool. It's a dominance-based elitist optimization algorithm that aims to balance both exploitation and exploration in the search space. And to calculate the objective functions, we use Energy Plus. The tool is integrated with Energy Plus through OpenStudio SDK. Energy Plus is the main energy simulation engine, and OpenStudio SDK allows us to build energy models. And the objective functions is the maximization of net energy consumption due to heating, cooling, lighting, energy use, and photovoltaics electricity generation, and the maximization of daylight autonomy. So daylight autonomy is the total number of hours that zones are illuminated without the need of artificial lighting. And for this, an asymmetrical Gaussian membership function is used that favors the positive part of the set point. You can see that the peak point corresponds to 1, and the curve is much more steep to the negative direction and less steep to the positive direction. The modeling of the building and the photovoltaic panels and the shading devices are as such. Photovoltaic panels are used on shading devices marked with red, and also at the rooftop, and these are defined by several design parameters. The conversion efficiency of solar cells on the shading devices is 17%, and their fraction of the surface area with active solar cells is 90%, meaning that 90% of this area is dedicated to photovoltaics. The cumulative value for the fraction of active solar cells on the rooftop is 65%, and the angle is 32, which is the optimal inclination for Ankara, which is the for which the simulations are run. Window wall ratio of zones are on all 4 directions are also part of the chromosome, and they maintain an aspect ratio of 1:2. And compared to after we run the optimization, after we develop the optimization algorithm, we comparatively evaluate the results on a case study. And 5 building forms, as you can see to the right, are selected with different aspect ratios. The aspect ratios you can see at the bottom of each form. The total floor area is the same. There are 6 thermal zones with internal loads, with different internal loads, and the windows are selected as high performance windows with U values, SHGC values and VT values different on north facade and the other facades. And you can also see the NSGA2 variables. What I forgot to write here is that the optimization algorithm was run for 50 individuals and for 70 generations, which makes 3,500 individuals in total being evaluated. And the optimization results you can see here for the 5 different building forms. And one thing I forgot to mention is that for each building form, the photovoltaics installation was marked in red. So those surfaces highlighted in red are those surfaces on which photovoltaics were installed. And to repeat, the vertical surfaces use either overhangs on the south facade, an overhang for each floor, and the east and west surfaces facades use vertical loops, which is found to be most optimal for these directions. And to the bottom you can see the Pareto fronts of each instance, each building form, let's say. You can see a very large shift between A and D and all the others. This is because the photovoltaic electricity generation is drastically different between group AD and BEC. Normally, if PV generation, electricity generation was removed, they seem to be much closer. And also one thing I should mention is that energy used is considered only for heating, cooling, and artificial lighting. And based on these optimal results, the Pareto set for each building form, several metrics of evaluation were selected so that we can evaluate which building parameters have an influence on this Pareto front. So the first one is regarding the form of the building, form compactness, meaning volume over surface area. the footprint of the building as well as the south facade area are meaningful metrics that, or meaningful parameters that we can build upon our evaluation. And the objective values, of course, as I mentioned, are regarding building energy performance, net energy consumption, and the photovoltaic energy generation, as well as daylighting performance. So in the paper you can see this table and the values. So the columns represent the building forms, different building forms, and these are different metrics that are used as a basis for evaluation. So several results, meaningful results that we can extract from these findings are as such. The first one is that PV electricity generation is most determinant in net energy consumption, and as I mentioned, this is the main reason that the Pareto sets were shifting so drastically. And I think I forgot to write here what the axes mean. So this is the net energy consumption and this is daylight autonomy. And photovoltaic electricity generation is directly proportional to the building surfaces made available for them. The maximization of the rooftop, for example in Form C, has a bigger impact than the maximization of the southern facade, although the whole rooftop area cannot be effectively operationalized for electricity generation. It's only 60%. The active solar cells constitute only 60%, 65% of the rooftop. And this image shows the performance. For example, Form C is the one that produced the most electricity from photovoltaics. The second one is Form E, B, A, and D respectively. So you can see that C1 was the best one in terms of performance, and the second one is Form E, which has very large surfaces for east and west facades. However, the high frequency of PV panels can increase PV electricity production. We should always consider that as we increase the shading devices, we will be producing more electricity. But the amount of energy generated per PV area does not justify its use at all. And in this case, their initial and life cycle costs need to be considered as well, because it might be the case that these photovoltaics are unnecessarily being used with abundance. And if we take a look at here, you can see that photovoltaics gain per PV area, the Form B, which has a much larger southern facade, outperforms E in this case. So E might produce much electricity, but when this is reflected on the number of photovoltaic panels, this really is not the case. And energy consumption is lower in buildings with either a large footprint and located or which have east-west direction. So compactness, form compactness, and orientation are key. And this is very curious because this completely justifies the rules of thumb of building design regarding building form of energy efficient buildings. And compact forms with less spatial depth perform better in daylight autonomy, and this is because their lighting energy use is lower. And again, southwest orientation has a negative effect on DA, daylight autonomy. Buildings with large footprints perform relatively poor in daylighting because these deep spaces pose challenges to be fully illuminated by daylight. And if this is the case, alternative solutions need to be formulated to introduce daylight into spaces. The further use of the tool that I presented could be for buildings or shading devices with increased complexity. So the case study that I showed was very simple louvers or overhangs, but in architecture, much complex geometries are being used increasingly, as you can see to the right. And also the tool can be used to dynamically control shading devices. Instead of fixed shading devices, these controllable shading system can better optimize the flows of heat and light energy than fixed solar shading systems. And finally, the future research direction that we plan to pursue is the efficiency or the building performance and efficiency of photovoltaics in climate change, in a changing climate. So the rising temperatures due to global warming, it has an influence on PV efficiency, because with higher temperature the efficiency seems to drop, and solar radiation is expected to increase in the future. You can see to the right the dry bulb temperatures, the daily average dry bulb temperatures for the current weather files, and the 2060 weather files under 8.5 climate change scenario. Probably it's not very visible, as you cannot horizontally compare these bars, but there is a drastic difference that we will experience in the following 45 years. A 5-degree difference is expected in Ankara. So how we can design now based on the climate files, climate data of the future is a further future research direction for us. And this was the end of my presentation.
Okay, thank you.